Okay, I think I'm recording. So the idea is, well, you can already see I have some plot here. Well, this is the plot which we want to get today eventually, but I will start from something simpler. So first of all, if you go on Canvas, I put on the 491 course, I put some data file there. I just wanted all of us to have an example of the same data file. You can download it. And if you have a Windows computer, I put a version for Windows, which is slightly different. We're not going to go into these details, but the version which I have for Mac, which will work for Mac or Linux, but probably for Windows, it will give you troubles. So download these file, put it in the directory where your scripts are, and we're gonna use it as an example for plotting. And let me start. So the example, you saw it, Maximov 2019, right? So we'll use these data. Well, these data comes from Max Maximov, my PhD student, from one of the papers he published in 2019. And this data is experimental adsorption data. Max didn't do experiments. He did some numerical processing of the data, but we will use these experimental data as an example. But before we go there, let me remind you that last time we started working with NumPy. Let's create a new script, and I'll start with importing NumPy, typically. Importing NumPy as NP. All right. And before plotting the data which we're going to need further, I wanted to show how we can plot some other simple data. So in order to do that, we will need to use another module which is called matplotlib, and we will use the pyplot, and for the sake of shortness, we're going to call it PLT. So once again, this thing, oh, and let me make it a little bit larger. All right, and here as well. This thing will let us use the math, and this thing will let us use the plotting. And let's start from something simple. Let's start from creating two NumPy arrays. First would be NumPy lin space. Remember what that is, right? So it's a linearly spaced points. Let's say from 0 to, I don't know, 3, and let it be, I don't know, 101 points. And then let y be x. Oh, let's take less points. Let's take 11 points. All right. Let y be x squared, right? And what I want to do, I want to plot this function, right? So the simplest way to do it, now when we imported matplotlib, the simplest way to do it would be plt.plot, and then we write x, y, and I think we need to show it also. Now it will ask me to save this file, which I'm gonna do. Okay. So let me call 05. It's our 5th meeting. Okay, simple plot. All right. And while I saved it, it already plotted me everything, right? Looks like a parabola, hopefully. So at the point 1, we have 1. At the point 3, we have 9 somewhere here. We don't see it on the axis, but it looks like it's supposed to. So obviously it didn't ask us for any options, right? It's like in Excel, when you plot something, it has some default formatting, and it will plot it in whatever formatting it thinks it is appropriate. I think, well, these digits are very small. I can barely read them. I don't know if you can read them. So the color, I don't like these blue color. I would prefer something else, and I want to have full control on my plot. So in order to do that, there are several ways how you can deal with formatting. I typically introduce figure and axis in the figure, and then use different options for that. So I'm gonna show it to you now, just in a second. Well, in fact, you can even, some of the options can be easily tuned here. So here you can say R, which will make the color red, or you can say K, which will make the color black. You can say K double dash, and it will make that dashed line, right? And so many other things. Well, the options, in fact, can be written in more transparent format. You can say color equals K line style equals double dash, right? And it will be the same thing. I can add markers as well. So currently it's drawing a line, but it doesn't show the points. Marker, forgot if it's plural or single. I think single, and let it be circle. Yep. So we had the lin space from 0 to 3 of 11 points. So it's showing us this 11 points and drawing a line in between. If we want to remove a line, we can just say line style is empty, and it will show just the markers. All right, so there are many ways to make the plot look how you want it to look. And in fact, there are you can write styles for these plots and so on. This is not something we will be specifically concerned about for now. I would like at least to make sure that you can plot the data and compare different curves to each other and so on. Because I just want to make sure, are you guys are all following? Am I going too fast? Is it fine? Is it no, not too fast? All right, good, excellent. So then I'm gonna continue. I want okay. I don't want to deal with these y equals x squared. That's too boring. In fact, what I want to do, I want to read the data from my file. Let me do that, and let me illustrate a little bit how, then using that example, we can illustrate some of the options for the plotting. Let me create a new script. Oops. Control N. Let me save it immediately. Okay, so let me call it Max's data. Okay, Max data, because that's the data from Max. Okay. And I start from the same thing, and you can copy and paste it in most of your scripts, but it would be faster to type it. So import numpy as in p, and import matplotlib.pyplot as plt, right? And the first thing I want to do, so now make sure that your file is in the right directory, because I will be reading these data file. I want to read the data file, which you downloaded from Canvas, and do something with the data, right? So let me call my data file, introduce a variable data file, and the file name was, what was it? Maximov. You can rename it if you don't like this long name. So Maximov 2019 sample1.txt. All right. And I need, so my data will be numpy load txt, and now while it gives me hints for the parameters I need to use, my file name would be data file. The comments, there are no comments. I need to skip the first row. If you open this file, it would be instructive to open the file. So I think I put it here. Okay. So if you open the file, look at the file. This is the data. Oops. This is the data you have in the file. So the first row has the information, which is what's in each of the columns, right? So this is relative pressure. This is absolute pressure in kilopascal, and this is amount adsorbed per gram, centimeter cube per gram STP. I'm going to later talk about what it is, and this is why I need a whiteboard today. But this is an adsorption isotherm. This is an experimental adsorption isotherm. And I want to admit that P relative and P absolute, well, you don't need two of them. One is sufficient. You either use absolute or you use relative. So I'm going to use just the relative pressure. And therefore, I don't need to read the second column at all. So I'm doing here skip rows 1 and use calls, which allows me to use only the columns I need, and then it would be 0 and 2. So I'm skipping that column number 1. All right, let me make sure that this works, and I can tell you it won't because I don't think I'm in the right directory. So if I run it, well, it says, well, oh no, I have a typo in the matplotlib. That's worse. Okay, it didn't find the file because I need to give a path to this file, and this file was where in scripts 0.5 adsorption. Okay, so 0.5 adsorption. Hopefully now it's going to work. Yep, now it worked. Make sure it works on your end. Make sure you put the file in the right place and read it, because if you didn't read the file, then it would be hard to proceed any further. Good? Can proceed? Okay. So we read the data from the file, and now we want the first thing to display the data. So I don't want to print this data anymore. Instead, I'm going to say that there are two columns. So my first column would be relative pressure. I'll call it P naught, meaning P divided by P naught, relative pressure, which will be my data first column, right? The second column would be, as I said, it will be amount adsorbed. It's an absorption isotherm, centimeter cube per gram. And this is centimeter cube STP. Absorption, just data. And I can begin with just plotting the data as it is. So PP naught on the x-axis and centimeter cube gram on the y-axis, and plot PLT show. All right. Plot is not defined because I have to say plt.plot. All right, I plotted my adsorption isotherm. Make sure you can do the same. And before going any further and dealing further with these data, I want to give you just a couple of equations related to adsorption. And the reason is, well, I mean, the purpose of these meetings is not to teach you numerical methods, right? The purpose of these meetings is to show you how to use Python, and in particular NumPy, how to use this as a tool to solve some of the problems related to your research. And well, since your research hopefully is related to my research, I want to relate it to some of the problem I've been working on. This is let me stop sharing screen here. I hope you got the isotherm. I'll get back to it soon, but before I do so, I want to okay, I want to write a couple of equations. So, well, the absorption isotherm, which you see, once again, some of you probably have heard these before at group meetings. This is something very, very commonly, very regularly discussed in our group meetings. While we're looking at absorption of different species on different solids, right? And the absorption isotherm means temperature constant, is amount absorbed, whatever, in moles, or typically it's moles per gram, and as a function of pressure or relative pressure if we're absorbing gas at subcritical conditions. So in particular, one of the very common application of gas absorption is application for characterization purposes. In fact, many of my colleagues, experimentalists, who work with different materials, one of the way to characterize materials is to measure the surface area, and the surface area is measured based on how much gas can be absorbed by the surface. So how many gas molecules stick to its surface. Obviously, if the surface is larger, the amount of gas absorbed is larger. So this is typically done with nitrogen at 77 Kelvin. It's normal boiling point, and the data I'm showing to you is in fact this nitrogen absorption at 77 Kelvin. And well, in this case, this plot, it looks something like that. Sometimes the curves look somewhat different depending on the pore sizes in the material and the pore structure. Sometimes it looks it can look like that, or it can look like let me take a different color. Okay. And it can look like this, and desorption would give you hysteresis. I'm not going to go in detail with that right now, but what I want to say that only a part of these data, while the part which I occasionally erased, is used for determination of the surface area. If this is 1, relative pressure equals 1, the region between 0.05 and 0.3, this region of pressure is typically used for defining the surface area. And the method which is used is the BET method. Has anyone heard of BET method before? No? Okay, that stands for the three names. So it's Brunauer, Emmett, and Teller. Let me make sure I spell them right. Teller, before I write it. Oh boy. Okay. Yeah, Brunauer, Emmett with the double M and double T, and Teller. And in these three folks, the third name you might have heard about. So if it's the same Edward Teller, who's famous for many other contributions to physics and chemistry. And did you hear these names before? Edward Teller? Yes, no? You can type something in the chat like we do in class. Just yes or no would be fine. Just curious. Okay. Okay. Yeah. So, well, Edward Teller was one of the leaders in the Manhattan Project. So it's worth reading a little bit about the 20th century history. It's more than just physics. So anyway, but Teller, well, one of his major contributions besides nuclear weapons, his major contribution was this theory of adsorption, very simple theory written in the 1930s, where they came up with a simple equation for amount adsorbed. So I'll call it n small, so it can be n capital or n small, equals amount adsorbed in a monolayer times C. I'll tell you what the meaning of C is. P over P naught 1 minus P over P naught 1 plus C minus 1 P over P naught. So this is very simple two-parametric dependence, a two-parametric equation, which is called the BET equation. So where N is amount adsorbed. So typically would be it would be something like moles per gram, right? P over P naught is the relative pressure, as I said, and M is the monolayer capacity. So how much gas is adsorbed in the monolayer? And C is a certain constant which determines the strength of interaction between the molecules of adsorbing gas and the surface, which is known as BET constant. So, and as I said, this theory is applicable typically not to the entire part of the isotherm, but typically to the low pressure region. And this equation allows us to calculate from experimental data I'll use this BET equation to calculate the surface area, which is called the BET surface area. And as I said, for many people who synthesize materials, and I can easily tell in our department, for example, Ed Drazen uses this method quite frequently. So he prepares different materials with specific properties he need. I know in chemistry department people use it. So we have an instrument in the York Center to do it, and it's a routine technique because you synthesize a material, you want to know how big is the surface area of it, is it? So why I'm talking about these BET method, besides that it's widely used and it's probably one of the most cited papers of Edward Teller, and the most cited papers, in fact, in all the chemistry overall. It's amazing. It's tens of thousands of citations. So the reason I'm talking about it is because I want to show you how with Python you can use your experimental data to curve fit, to extract certain parameters from the equations. And well, instead of doing just a simple dependence which doesn't have any physical meaning, I would rather take a function which has a meaning for me. So if you took the BET if you take the adsorption data and represent the BET equation in the following form, so 1 over n P naught over P minus 1 equals 1 over n monolayer times C plus C minus 1 over C n monolayer P over P naught, you will get a simple linear dependence, which is perfect for curve fitting. So in this, and I'm skipping the details. I will ask you, in fact, to go and make sure you can get from the original BT equation, you can get to this equation, right? Derive it. Not now. You'll have time for it. But this is your function. This is your, let me call it y. This is your intercept, and this is your slope. If you plot your function y as a function of p over p naught. So I can further, again, I'm going to skip the detail, but from here you can show that the capacity of this monolayer, the amount of gas absorbed in a monolayer, is 1 over slope plus intercept, and the BET constant is 1 plus slope over intercept. Well, and that's all I needed for now about the BET equation. I will need to add a few more details because, well, we calculate the amount absorbed in monolayer, but we would need to translate it to surface area after that. Well, I can say how we can do it. So assuming, so this is a surface, right? This is a surface of a material. And keep in mind, when I'm saying, we're measuring the surface of the material, of course, it's not a plane, it's not like a sheet of paper, right? It's not a sheet of metal. The surface area of this object, first of all, is very easy to measure. Second, it will be very small. We're talking about materials with porosity. Of course, the material, we have a lot of pore space, and when we say surface area, so we're looking at the tiny little sample, which is all could, have 50% porosity or whatever, 30% porosity, and these pores are tiny, and each of these pores correspond to the overall surface area. And the values, it's quite impressive. The values for surface area could be hundreds to thousands meters square per gram. So 1 gram of material giving you several hundred square meters of area, right? Like a soccer field. If you imagine that your molecules, and nitrogen molecules, well, nitrogen is diatomic, but if you imagine it as just simple spheres, it can fill the surface densely, right? And you can write the cross-section area, let me call it to distinguish it easily, like S small of nitrogen molecule can be obtained, and well, this is something which we can use further to calculate from the amount absorbed on the given surface to the surface area. So we'll need this number further. All right. So this is, well, for now, this is all the basics of absorption we need to know, because we're going to go back and do our, well, data analysis and curve fitting. Let me stop sharing the screen here. Okay. And get back to my screen here. Any questions so far, by the way? Nope. Okay. All right. So I hope you will have your equations in front of you. I will try to have it in front of me as well. And let's get back to our data. Oh, the first thing, as I said, these experimental data, it's not that I said that, this experimental data was in not in moles, right? We typically measure the amount absorbed or any amount of matter in moles, but it was not in moles, but it was in centimeter cube STP. Is anyone familiar with those units? Yes or no? Oh, I don't see the chat here, unfortunately. Oh, this is okay. No, that's not as no, that's not CGS. No. So what we need to do, so it's the centimeter cube STP is the centimeter cube, well, volume, which takes the gas at STP conditions, so standard temperature pressure. So you need to take the ideal gas equation of state and recalculate the volume into number of moles. And this is the first thing which I'm going to do, because in fact, I don't want to deal with these centimeter cube STP. I want to deal with moles, right? So let me comment these out. We don't need it yet. And the first thing is, well, I will need STP conditions, right? So this is STP conditions. Pressure equal 1 to the 10 to the power 5, of course, in Pascal. Then temperature is 273.15 Kelvin. I need the gas constant, R, which is 831. I can add one more digit here, right? Joule per mole per Kelvin. I'm writing these comments for myself just to make sure I'm using the right units everywhere, because making a mistake, bars to instead of pascals will give you 5 orders of magnitude difference in your results, which would be sad. So the first thing I want to do is I want to say N in mole per gram would be, and then I use what I need to do. Let me write it as a comment here. So I want to have P times V equals N number of moles times R times T. So I'm expressing my N from these equation, from the ideal gas equation of state, right? So N moles in grams would be P times N in centimeter cube per gram divided by R times T. Is that it? Is that right? Would it give me the right thing? Would it give me the amount in moles? Will it? I don't see the chat here. Let me. Okay. You're not saying anything in the chat. Say something. Will it give me moles or will it not? Difficult question. Well, it won't, because I have here centimeters cube instead of meters cube, right? And everything else. Yeah, I need to convert centimeters cube to meters cube, and then I will get moles. So I will need to divide by 10 to the power 6. And that's just the first step. That's what will give me the conversion to moles per gram. And then, well, I can do it moles per kilogram, but I can leave it in the per gram basis. So then the next step, well, now getting more to dealing with the data. So as I said, we can introduce a function of these data which would look like, oh, let me plot these data again. All right, so N in moles per gram. Yeah. This is still the same isotherm, right? And as I said, we will be looking just at these regions, so at the region at the low pressures, where we have this monolayer coverage of the surface. So let me make the next step. The next step would be to express these BT function. So introduce BT function. I'll call it just y. I won't come up with a better name. And if you look at the equation which I have just written, it would be 1 over amount adsorbed. I'll call it n mole per gram times 1 divided by p naught minus 1. All right, and I think that's if this is the correct form. Let me plot it. Let me plot now this thing. Okay, well, it gave this behavior going to pretty much infinity, but I don't care about that part. I care only about the part here. And in order to do that, I need to select my data so that I'm considering the pressures only in this region. Let me call it P left is 0.05 and P right equals 0. It's either 0.3 or 0.35 for this region. And I want to find the data. I want to take not the entire data. And by the way, I can, let me do one more thing. When I plot it, let me add the markers. Marker equals just the dots, so that you can see there are a lot of data. It's a huge number of points, right? So I want to take only those points which are between 0.5 and 0.3, 0.05 and 0.3. So I will use the indices for, well, which I call fit ind equals, and I remind you last time we were discussing these function where, right, the numpy where, so it defines the set of indices where a certain condition is applicable. And let me write it as numpy logical and I need the indices where my pressures are either not either, but are at the same time higher than P left, and my pressures are lower than P right. So I can look, let me just print these indices just for myself. Okay, fit ind. All right. Yeah, so it's printed me this array from 11 to 20, so it's 10 points. Well, that's certainly sufficient for the fitting. And now I can say that I don't want to deal with the entire P over P naught and Y, but I want to take some subsets of these data. So P naught, F, well, this F stands for fitting. This is what I'm going to be using for fitting. Would be P naught of fit and Y. F equals Y. Oh, sorry, ind fit. All right. Well, fit ind. Okay, I called it differently. Sorry. Okay, I'm still plotting the same old curve. Now I want to update it and plot it with P naught F versus Y F. All right, I'm plotting just this data. Do you need a minute to catch up, or are you able to follow? Let me move my screen here a little bit so that you see the entire thing, and also Worked? Yes, Sydney, it looks like it worked for you. All right, guys, I hope everyone else is also able to follow. Okay, so what I want to do now before, well, I will do some other manipulations. When I see a plot with the axes which are not labeled, it annoys me so badly. I can't tolerate it. So before I proceed with the further manipulations with the data, well, in particular the curve fitting, I want to label everything in my plot. So how I typically do it, and as I said, there are several ways to do it. I introduce a figure, a new object, plt.figure. So then I introduce axis because I will be making many different manipulations with the axis, labeling them in particular. So add subplot, oops. And in fact, well, you don't necessarily need subplot, but with subplot you can make, well, more than one plot within one figure. But here let's take one plot for now. So then I can, instead of doing plt.plot, I will do x.plot. And then, well, the axis labels this is what I needed very badly. X set X label, and let me call it, well, I'll call it Y, okay? And this is X set Y label. Oh, no, this is my x-axis. So x-axis was P over P naught, and the y-axis is Y. Okay, and hopefully it will work. Yep, it works, and now I have my axes which are labeled. While the parameter y, it actually has units if we think about it. So this part was dimensionless, but this was in moles per gram, so it's grams per mole. So I can even say here gram per mole. All right, so to be even more rigorous. All right, and now let me show you a little bit more control. As I said, well, we can use here the marker, and we can control the marker. Let me make the cross as a marker. Let me make the line style as empty, and let me make the color as, I'll let it be red. Okay. So I like it a little bit more that way. So this is the data from our experimental adsorption isotherm for the pressure in this range, which we will further use to get the BT surface area. And this is another feature of NumPy, which I wanted to show you because NumPy can do the basic curve fitting. And well, in this format, it's obviously a linear trend. So NumPy has a function Polyfit, so which can fit your data to a polynomial. And I will continue here before my figure because I want to show my fit on the figure as well. So I will add here this curve fitting. Let me start. So NumPy, NumPy poly fit, and then the first argument would be my x, which is p naught f. The second argument would be my y, which would be yf. And the third argument would be the degree of my polynomial. And what the degree of my polynomial will be here? would be 1, right? So it's a linear fit. Yep. So that's a very straightforward case. And the parameters which this function will return, so the first two parameters will be slope and intercept. I'll call them slope and intercept. It can return more, it can return r squared and so on. Well, not for now, just now I care about slope and intercept. And then let me introduce a function y linear, right, which I will base on my obtained slope and intercept. So I take the values of my slope multiplied by the values of my x and add here my intercept. So this will be the linear fit to my function. And in my plot, I want to add the plotting of not just the experimental data, but also to these data obtained from fitting. PP naught F Y linear. And I want to use no marker for it. So marker is empty, but I want to use a line, which will be dashed line, and the color will be blue. All right, I got a nice linear fit for my data. And well, that illustrates first how I deal with my well, reading the data, doing manipulations with my data using NumPy, doing a linear fit with NumPy. And as I said, it doesn't have to be a linear fit, so it's polyfit. You can use different functions for your fitting, and then using different options of your plotting. One more thing which is worth adding is labels, right? I want to label. This is experimental, and this is modal, and I need to add the legend here. So AX legend, and the legend has an option of location, and I think you can just make location best, and if I'm not mistaken, yeah, it will figure out where to locate it. All right, so the last thing to do would be to calculate the BT surface area. If this is, well, besides the curve fitting itself, if this is what we wanted to do. So let me add this calculation here and wrap up with that. So the formulas I gave you, which I will ask you to get yourself, was that the capacity of the monolayer was 1 over S plus I. Then the BT constant. Oh, in fact, you know what? I don't need a BT constant. BT constant is important to quantify the strengths of interactions, but not the surface area. So for the surface area, all I need to introduce the Avogadro's number. And I need to introduce this number as small, which is the area of one molecule, right? So this will be 0, 162 e to power minus 18, minus 18, because that was nanometer squared, right? So now I'm writing it in meters squared. And I write that my SBT, the BT surface area, is the amount adsorbed, while this is NM, the amount adsorbed in the monolayer, times the area each of these molecules take, right? So this is the area each of these molecules take, and I need to recalculate from moles to number of molecules. So I multiply this by Avogadro number. And the last thing I want to do, I want to print my dt surface area, which will be in, if I did all the units correctly, that will be in meters squared per gram. So SBT in meters squared per gram. And let's see what I get. All right, well, I should have taken care of the formatting, but overall, this is a very reasonable number. So this porous sample, which I used in these experimental data, it's actually a synthetic opal. It's a silica sample. It has the specific surface area of 31 meters squared per gram, which is relatively low because the pores are relatively large. So some microporous materials can easily exceed these by 1 or even 2 orders of magnitude. And that's all I wanted to show you today. Let me just stop the recording and I'll let you ask some questions.